Hello, everybody. So today, in this video, we're going to talk about a new mathematical object. Maybe you've seen it somewhere in the past, but I'm going to consider it mostly new. And so what we're talking about are things called vectors. Okay. So there's a lot of different ways we're going to come to think of vectors, but let's just start with some kind of a notion of a definition. It's going to be an object with magnitude and direction. Okay, so it will be pretty obvious, at least after some examples, why we need things like this. There are a lot of things that are described not just with a size, but also direction, right? Numbers can tell us a size. So things like weight, right, just give you the magnitude of something, or energy, right? That's an amount of something, volume, those kinds of things. But when you want to describe something like velocity, right, we're talking about not just how fast something's going, but also what direction it's going in. Right, that would change a lot of, if you're trying to do a physics problem, the dynamics of the problem, depending on what direction something's going. Or force, right? Not just how hard am I pushing something, but what direction am I pushing it in, right? Those sorts of things. So that's what vectors are going, one of the reasons we use vectors. We name our vectors. There's a lot of notations for it. In a textbook, you might see bold. I can't really do bold. So what people often do is, if I'm naming my vector v, they might write v with a little arrow on it, or sometimes even just a line, mostly out of, let's say, efficiency, because it can become cumbersome to write that over and over again. It should be clear from context once you get used to them. Undeniably, it can be a bit confusing in the beginning to figure out, what am I looking at here? Is this a vector or a typical number? We'll often call numbers scalars in the context of vectors. We can also represent them geometrically, and the typical way to do this is with an arrow, right? So that might be the arrow V, right? And with an arrow, right, the length of it represents the magnitude, and the direction of the arrow represents the direction, right? And so if I was, if this was representing a force, let's say, maybe somebody else is pushing in the same direction, but they're not pushing as hard, I might represent it with this arrow. It's going the same way, but not as large, right? So we get our magnitude and our direction both with these arrows, right? And we'll consider vectors. If I drew another vector over here, let's call this one u, right? And pretend that I'm very good at this, and these two have exactly the same direction and the same magnitude, then we would say that u and v are equivalent, and we might write u equals v to consider, and we'll consider them the same thing. Right? There are some technical contexts where you might have to start thinking of them a little differently, but we're not going to come anywhere close to having to worry about that. There's just going to be a lot of, we're doing a lot of setup, right, for vectors, so I'm just warning you, there's a lot of vocabulary and definitions coming here. We'll call the beginning, right, of this vector, this point here, the initial point. And we'll call the point at the end of this tip the terminal point. Maybe that's too many arrows going on. Right, so right here is our initial point, out here is our terminal point of the vector, right? We tend to think of vectors going from here to there, right? So if I had 2 points labeled in the plane, or it could be in 3 dimensions, in fact, vectors work in any number of dimensions, I would say this vector has the initial point at A, terminal point at B. I don't know, I'll name this vector X. Sometimes people write this to mean starting at A, going to B, okay, or the vector from A to B. We'll also note the 0 vector this way, and this is just a vector. There we go. This is just a vector with no magnitude and no specific direction. Okay, it's the only vector that doesn't have a specific direction. Okay, so we want to be able to do things with these vectors, and so we're going to start by talking about how do we add vectors. We're going to start with a geometric interpretation of addition of vectors. So let's just say I have 2 vectors. I'll call this one V, and let's make another one something like this is U. Right? So there's 2 vectors. I want to add V plus U. Okay. So what I'm going to do, I'm going to start. I'm going to draw V again. And then I'm going to take the initial point of U and move it to the terminal point of V. So imagine just sliding this over here. So I'm placing U in this way here. Okay. The vector V plus U then is going to be this one here, connecting now the initial point of V to the terminal point of U when we place it this way. Okay, right. This here is a new vector, V plus U. Okay, we got it by combining these 2 vectors, but it is its own thing. Just like 2 plus 7 is a number, right? Just because we got it to 2 plus 7 by combining 2 and 5, we're ending up with a number, a single number 7, right? This is a vector. I could give it a new name if I want. I'm just going to leave it V plus U for now. One thing we should also notice about the geometry here, suppose I took U, I'm going to make a copy of U and place it right here. So I'm starting the initial point of U where the initial point of V was. And then I'm going to put, so here's a copy of U, and then I'm going to put V right here. Again, pretend that I'm very, very good at drawing these things perfectly the same way each time. We end up in the same place, right? You can kind of think about it as a parallelogram. These 2 copies of V are the same direction, like 2 sides, the parallel sides of a parallelogram. U are the other 2 parallel sides that are the same length and direction. So we end up with the same vector. This one we might think of as U plus V, which gives us this notion that U plus V is equal to V plus U, right? Which is nice. That vector addition commutes, meaning you can change the order, okay? It might seem obvious, however, we're going to see some things in the coming videos that don't commute. Certain kinds of multiplication of vectors don't commute. We're a little ways away from getting there, but it's not trivial that we have this fact. It's a good and nice property of vectors. I don't know what good means in that context. Nice maybe just means it makes them easy to work with. Okay, let's use our notion of addition to come up with a notion of what we'll call scalar multiplication. So think about what happens when we add numbers. If I take 5 plus 5, right? One thing I can think of this as is 2 times 5, right? Multiplication counts how many times I add something up, right? If I had 5 plus 5 plus 5, it'd be 3 times 5, right? So I want to use that context for multiplication. It counts, it keeps track of additions for us. Well, let's do that with vectors. If I have a vector, oh, let's do a new one. I'll just call it A. And let's just add a copy of A to itself, right? So remember, I'm adding A to itself, getting A plus A, right? Well, it's just take the initial point of A, put it at the terminal point of A, right? This other copy of it. And our new vector, I should be drawing it directly on top of this, but I don't want to make the drawing any more confusing than it is, right? It's going to be the same, it's going to be a vector just in the same direction as A, but twice as long, right? We keep moving that way. Well, this idea of multiplication, counting, addition gives us an idea of how we should think about scalar multiplication. A plus A is just 2A, right? The number of times I added up A. And what did we end up with? We ended up with a vector in the same direction as A, twice as long. And in general, that's what we'll use for our definition of scalar multiplication. Let's say if C is a scalar, and all I mean by this is a number, then C times the vector A is a vector the absolute value of C, no, let's say it this way, a vector whose length is the absolute value of C times the length of A, and it's in the direction of A if C is positive, and the opposite direction if C is negative. Okay, so that's going to be how we think about scalar multiplication, right? So if I took away A, if I multiply by a negative number, it reverses the direction. Okay, and notice, right? We multiplied by 2, so we get a vector twice as long. If I multiply by half now, we can expand this. It's going to shrink the size of A to half the length, or whatever length you want to do, right? So let's just do a quick example of that geometrically. So let's say I have a vector V. If I multiply V by 1/3, I get a vector in the same direction, so approximating about 1/3 of the length of this one. I get a vector like this. And if I did something like negative 1/3 V, I get a vector like that, right? Again, pretending those are 1/3 of the original one drawn, okay? This also gives us a nice intuition for the idea of parallel. We will say that two vectors, U and V, are parallel if U equals C times V for some scalar C. Right? So if I can multiply one by some number to stretch it and possibly reverse its order in order to make it identical to the other one, then they're parallel. Otherwise, they're not, right? And this diagram essentially shows this. Look at if I had called this vector U, but noticed it was in the same, but noticed that I could multiply 1/3 of V to get the same vector, they must be in the same direction, only differing by size, right? Whereas on the other hand, if I have a vector U like this and V maybe going this way, there's no way I can scale one of these to go in the same direction as the other, right? All we'll do is stretch and expand or contract the vectors that we have, okay? So that's our definition of parallel vectors. They're only vectors if there exists a number C so that they are equal. One of them is the scalar multiple of the other. Okay, so let's do a little bit more. This idea of scalar multiplication that we came up with, where if C is less than 0 or in the opposite direction, helps us understand how to think about subtraction. Okay. So we would say if I have a vector V call it this. Then negative v, right, which I can think of as -1 times v, is the vector v scaled by 1. I haven't changed the size, but it's just pointing the other way. Oops, that's my negative v. And so now if I have the vector u, let's make u go like this. Let's try to do u minus v. With this idea in mind, I can think of this as u plus negative v, right? So what do? I start with u. There's u. And then I add negative v to it. And I know how to add. Here's negative v. I know how to add vectors. I take the initial point of v and place it here. And then this is negative v. And the vector I get is the one from the initial point of u to the terminal point of v. This is going to be the vector u minus v. Okay. All right. So that gives us an easy way to think about subtraction of vectors. Let's do one other thing with this. This drawing gets a little bit ugly. Let's take the vector v. Let me see if I can do this well. The vector v here's the vector v. Trying to copy this vector here still. And I'm going to add this vector to it. U minus v. So I'm adding this vector here. It looks something like this. I should have written this on the other side. Well, the vector in here, so this red one is u minus v. Let's just get rid of this. This is v here. This vector here is u, right? Which makes sense. What have I done? I started with v and added u minus v to it. Right? And while we haven't, oh yeah, we have enough stuff to show this. And so the minus v and the v here cancel, and we end up with just u, right? Which also shows us the vector u minus v is the vector between the endpoints, the terminal points of v and u when their initial points are aligned, right? It is the difference between them. What's the difference between these two vectors? It's this distance here, right, in this direction, okay? So it's a nice sort of geometric interpretation of what subtraction of vectors is telling us. Okay, so you might guess that we are not going to stick with drawing pictures to solve math problems. So what we want to do next is move this stuff into our three-dimensional coordinate system, okay? So let me try to draw our three-dimensional coordinate system. I have my z-axis, my x-axis, and my y-axis, okay? And let's say I have a vector v, and I'm going to draw it. So remember, think of this as the corner of the room, and I'm just kind of drawing a vector going out into space. So I'm going to try to help us see where I'm imagining this thing. Imagine moving, let's go a units along the x-axis. Then we're going to move b units parallel to the y-axis. So this distance here is a, this distance here is b, and then I'm going to move c units up. Okay. So you can imagine there were, if you put the shadow of the tip of this thing, it would be somewhere out here in the plane, and then it's c units up, right? In other words, this is the point A, B, C. Well, we will use these coordinates to define, this is my vector v, what we call the components of v, and they are just a, b, and c, right? So what we do is for any vector, right, and I'm doing it in 3 dimensions. This works with 2 dimensions. Vectors can be 2-dimensional, right? You can imagine drawing a vector in the plane, and it would have an x and a y coordinate. It's harder to imagine drawing vectors with more dimensions than this, though we can formulate all the math we need to formulate around them, and it works perfectly fine. But in any event, if you place the vector with its initial point at the origin, the coordinate point where it lands, right, where its terminal point is, we take those coordinate points and call them the components of the vector, and we write this way, right? It's very related to the coordinate system, but to keep it different, right, to keep these ideas separate, we use these angled brackets. We won't do this, our textbook doesn't do this, but you may see things like this. Right, there are some places that write it this way. This is because this is very related to linear algebra and matrices, and sometimes vectors can be thought of as a certain kind of a matrix, but we're not going to worry too much about that. But if you're reading about them and see this somewhere, then no, you're talking about the same thing, just written a different way. So the vector, while related to this point, is strictly a different thing than the point, right? A point doesn't have length, doesn't have magnitude or direction, it's just sitting there. The vector does, right? This represents the arrow that sits from the origin to that point, the thing with magnitude and direction, right? Now, if I move this vector around, right, wherever I put vector v, right, if I moved in some direction parallel to the x-axis a units, b units parallel to the y-axis, and c units parallel to the z-axis, I would still get to that, right? All that you could, imagine making metal bars in all these directions connecting to this vector. I could move that anywhere, right? So the arrow doesn't have to be at the center, but this is kind of an easy representation to see where this to see where these components come from. Okay, so it's measuring how far this vector moves, y direction, x direction, and z direction. So let's see, one more thing. Oh, I wanted to mention, when we do place it at the origin, we call it the position vector, right? We call it a position vector, I suppose. One of the things we'll do a little later with vectors is we'll move into vector functions. And so you can imagine maybe that there's a function that instead of spitting out numbers, right, x squared, you put in a number, you get a number out. Now we're going to have functions that spit out vectors. And you can have a position function that just keeps pointing at where some object is, right? If you imagine a series of vectors pointing from the origin, maybe there's a satellite circling the Earth, and make the origin wherever your station is. You could have a vector function that just keeps pointing at your satellite, right? So that's maybe the notion of why we call it a position vector. From wherever you consider the origin, it points at the thing you're interested in. Let's think about putting these vectors somewhere else. So suppose here's a point, let's call this point x1, y1, z1, and there's another point x2, y2, z2, and let's imagine the vector between them, right? Well, you can imagine all we want to do if we want to measure, we want to imagine if we moved it to the origin, how far, what would the coordinates be? Well, the a coordinate is just, if you start at 0, how far does the x coordinate change? Well, now instead of starting at 0, we're starting at x1, so how far the x coordinate changes is x2 minus x1. Okay, so I'm still calling this v. How much does the y coordinate change? y2 minus y1, z2 minus z1. right? And these become our vector components. So even if our vector doesn't start out centered at the origin, we can still figure out what its components are based on the 2 points it spans, right? So let me say that again. The notion of these components is just measuring, right, when we start at the origin, how much displacement is there in the x direction as you move from the beginning to the end. Then how much displacement is there in the y direction, then the c direction. We can do the exact same thing, displacement in the x direction, displacement in the y, displacement in the z, to get the components of the vector, right? And so you'll get your 3 numbers this way, all right? All right. So let's see. Let's run through a few properties of vectors now. So most of these I'm going to draw in 2 dimensions because it's easier, but these all apply in any number of dimensions. So first of all, let's think about the magnitude of a vector. So if this is the point x1, y1, and this is the point x2, y2, if I want to know the magnitude of the vector between them, I could just find the distance between these points, and we already have a formula for that, the distance formula, right? The distance between these 2 points is x2 minus x1 squared plus y2 minus y1 squared. Right, that's just our distance formula. Oh, excuse me, then we take the square root of it. So in terms of my vector, that's just going to be the magnitude of this vector, which we write with the symbol. We say this, the magnitude of V, right? It's the absolute value bars, but we think of them as, they really are best thought of, I think, in my opinion, as like a distance operator, right? They are the function that spits out the distance in whatever context we're talking about, right? If you have a number and you take its absolute value, you're getting its distance from the origin, right? Here you're getting the magnitude, right? The distance this vector spans, okay? So that's our symbol. Notice what we have here though. These are just the components of the vector. I did it in 2 dimensions here, but the same thing works in 3 dimensions. So what we can say more generally is that the magnitude for vector V, let's say it has components V1, V2, V3, the magnitude of V is V1 squared plus V2 squared plus V3 squared. Right? And if you had 4 dimensions, you can add a 4th component. If you have 1,000 dimensions, you can have that, and that stuff happens. Or in 2 dimensions, you have just 2 of them, like we did up here. You can even think of this in 1 dimension. It defaults to our notion of absolute value, right? A 1-dimensional vector just has 1 component. And if you square the number and then take its square root, you end up with the positive of that number, whether it started out positive or negative. So it expands rather nicely. Okay, so that's our notion of magnitude. The magnitude of vector V is the square root of the sum of the squares of its components. Okay, all right, let's do another geometric interpretation in 2 dimensions and see how we can expand that to algebraically and into 3 dimensions. Let's say I have 2 vectors, U and V. Let's give them components. I'll start with them being 2-dimensional for the purpose of drawing. So let's say this is U, and then I'm going to add V to it. And let's make V something like okay. And I want to find out what is U plus V, right? I already know it's this arrow between there, but what about in terms of components? Okay, U plus V. All right, let's think about its first component, right? the first component, if we're dealing in 2 dimensions, is just how far does this new vector move in the horizontal direction, okay? Well, first we move the exact same distance horizontally that you moved, right? I'm ignoring the vertical magnitude now, any vertical change in this vector. But horizontally, u goes this far, which is captured by its first component, right? Then we move the same distance v moves. In the way that I've drawn it, it looks like it's in the negative x direction, right? So if I moved 5 units positive and then 2 units back, I would have 5 plus this would be a -2 component. I would just add the distance in the number in the v component, right? And the same thing for our vertical displacement for this vector, right? So it's a very simple way that we can add vectors is we simply add their components, right? It's about as easy as we could have hoped for, and geometrically it makes total sense, right? If one vector moves 3 units, let's say the components of u were 3 and 1, and then v were something like -2 and 1, well, we would move 3 over, 1 up, then -2 over, so we'd be a total of 3 over, 2 back would be 1 to the right. We moved 1 up, we move 1 more up, and we'd be 2 total units up. And adding these components, 3 and -2, 1 and 1, would give us exactly that, okay? So in 3 dimensions, we would just say for u equal to u1, u2, u3, and v equal to v1, v2, v3, then u plus v is equal to u1 plus v1, u2 plus v2, u3 plus v3, okay? And let's do one more thing, and then we'll do a bunch of, we'll do a few examples here. Right? In a similar way, if I scale something, right? So let's use the same vector u that we have up here. If I take, well, let's do a new page, then we'll do examples of all these. If I take the vector u equal to u1, v1, let's say I scale this. So here's u, and let's say I scale it by some number. I'm just going to make it bigger for the sake of drawing, right? Let's say that looks like I about doubled it, right? Well, let's think about it in terms of components. Originally, u went a distance of u1 in this direction. Oh, sorry, this should be u1, u2, not u1, v1. I'm going to stick with the same notions. So, and then it moved u2 up, right? Well, this new, right, let's think about geometry here. This new vector is a scaled version of this in the same direction. These are going to be similar triangles, right? They're both right triangles. So if you make the hypotenuse c times as large, these 2 sides have to be scaled by the same amount. So that means cu is just equal to c times u1, c times u2. Right? And then in 3 dimensions, if u is equal to u1, u2, u3, then c times u is equal to c u1, c u2, c u3. Okay? All right, that was a whole bunch of stuff. Let's summarize what we have and do some examples, right? So we can boil this down to a shorter set of rules. Okay, so let's say it this way, that for a vector between points, let's say from point x1, y1, z1 to x2, y2, z2, is x2 minus x1, y2 minus y1, z2 minus z1. All right, so that's how we get, if we have 2 points and we want the vector between them from the first point to the second point, we take the difference of their components, the second point component, or their coordinates, the second coordinate minus the first coordinate in each component of the vector, okay? So that's how we get our component form of vectors from points. Then let's say, given vector v equals v1, v2, v3, u equals u1, u2, u3, and let's say we have a scalar c, then we have the following. The magnitude of v is the sum of the squares of its components. V plus u is just the sum of their components as each component. Oops, comma, v3 plus u3. Okay. And a scalar times a vector can just be the scalar times each component. All right, so let's do examples of all of these that hopefully help us see why this is all true. So let's start with, let's say, let's do it this way. Let's get a new paper. Let's find the vector from -1, 3, 2 to 4, 4, and -1. So these are 2 points in space in our 3-dimensional coordinate system. And if I want to find the component of the vector between them, I'm going to subtract, right? So I'm looking at this. Let's name this vector v. V is going to be 4 minus -1, 4 minus 3, -1, oops, -1 minus 2. So v is equal to 4 minus -1 is 5, 1, -3. So there's my vector. Okay. Let's compute the magnitude of v. This is going to be, right, again, I'm looking at this. I just take the sum of the squares of these components, 5 squared plus 1 squared plus -3 squared, which is going to be 25 plus 1 plus 9, which is the square root of 35. So this is a vector the square root of 35 units long, right? So just under 6 units long. Okay. If we have another vector u, let's let u equal 3, -1, 7, oops. Then v plus u is equal to, so now I'm just adding the components. 5 and 3 gives me 8. 1 and -1 gives me 0. -3 and 7 gives me 4. That's our new vector. Okay. And then finally, let's make a scalar multiple of v. Let's try 2v is just going to be equal to, and sometimes people will write 2 times, and now I've got my component representation. 2 times 5 is 10. 2 times 1 is 2. 2 times 3 is -6. Okay. All right. So that's just some of the algebra of vectors. Let's do one more example in a similar way, but with 2 dimensions that I think will help us see some of this a little better. And we'll just have to, I think it's way too much for me to try to draw it in 3 dimensions. But in 2 dimensions, we should be able to pull it off. So let me do one more example like this. So let's say I have the point, let's call this the point 2, 1. Let's move, let's go. Let's say this is the point 5, 3. My scale might not be perfect. And I want to get the vector between these 2 points. Let's call it W. Okay. Well, W should be equal to 5 minus 2, 3 minus 1. Vector 3, 2. Notice what that means. I'm going over 3 units and up 2, right? If I placed it at the origin, it would land at the point 3, 2. We just didn't happen to start at the origin. Okay. So what is the magnitude of W? Well, it's the same as finding the distance between these 2 points. When you find a distance, you subtract the x-coordinates and square them, subtract the y-coordinates and square them, add them up and take the square root. We've already done the subtracting part, so all we need to do is the square them and sum them up. 9 plus 4, W has the square root of 13 as its length. Let's add another vector to the mix. Let's put one, let's have the vector V equal to 1, 1, right? So we can imagine if I had it at the origin, it would look something like this, right? Pretend that was drawn a little better. That's the point 1, 1. That's the vector with components 1 and 1. So if I were to add W plus V, on this picture, right, I'm putting V at the tip of W, right? And what does V do? Moves over 1. I know my drawing's a little off, and up 1, right? That's what V does. So what does that mean we've done 2 total? If I were to draw the vector connecting them, it's moved over all this way. The 3 units that W moved over and the 1 unit that V moved over. So that's our 3 plus 1. Then it moved up the 2 units that W moved up plus another one for V. This is where we get this adding of components. So this new vector is the vector for 3. Okay. Finally, let's scale W. Let's scale it by 1/2. 1/2 W is equal to 1/2, just rewriting this in component form, which we can think of as 3/2 1. Okay. Let's go to that picture. Let's go to our picture here. If I started at this point and moved over by 3/2, I would move to, starting at 2, I would move to about here. And then I move up by 1, so about half this distance. It certainly appears to be about correct, right? Let's check our assumptions, right? According to our rule, this should be a vector half as long as W in the same direction. Let's start with the direction part. So I have these 2 vectors. Let's pretend, let's think for a moment about, let's place them at the origin. Here, let me go to new papers to do this. So here's what we have right now. We'll use this in a moment. We have a vector W is equal to 3, 2, and we have half W is equal to 3/2 1. So first of all, let's see if they're really in the same direction. And here's a way I think might help to do it. If I imagine placing the vector W, for instance, at the origin, we've already said it should land at the point 3, 2. I can imagine that W, right, lines up, it's sitting on some line. What's the slope of this line, right? Slope is one way we think about talking about the direction of a line. Well, I could just compute the slope. It's going to be the change in y, 2 minus 0, because I'm starting at the point 0, 0. 2 minus 0. So I'll call this m1, the slope of the line that W sits on. 2 minus 0 over 3 minus 0, or 2/3. The slope for half W will do the same thing. 1 over, or 1 minus 0, right? I don't want to draw it on top of this, but 1 minus 0, we would do the same idea. There'd be some line that it'd be lying on. 1 minus 0 over 3 halves minus 0 is equal to 1 over 3 halves. We multiply by the reciprocal, we get 2/3, right? So if we believe our notions about slope, that slope tells us about the direction lines go in, then it seems like the vector we just came up with does indeed land in the same direction. Let's check the length, okay? So we computed last time, but we'll just do it again. The magnitude of W is the square root of 9 plus 4. The squares of these, 9 plus 4 is 13. So we get the square root of 13. Let's compute the magnitude of half W, our new vector. It's going to be the square root of this squared, so 9/4, plus 1 squared, or 1. This is the square root of 9/4 plus 4/4, which is the square root of 13/4, which is the square root of 13 over the square root of 4, which we can write as the square root of 13 over 2, or exactly 1/2 the square root of 13. And so the length of this vector is exactly half the length of the original vector, as we expected, okay? Okay, let's stop there. That's a whole ton of stuff. We've still got a few more of what we would call vector basics, just laying the general landscape and how they operate and the algebra of them, but I'll save that for another one. All right, thanks everybody. I'll see you next time.